Hello, class. Today we're going to talk about proof by induction, and this is a type of proof that if you take higher level upper division math in college, you're going to be doing a lot of. And if you ever take, if you want to be a math teacher and you ever take one of the, or at least I had to take a test, and a lot of the proofs were this kind of math. And otherwise, it's just a really good way of thinking about things. And I want to start out with Fermat numbers. Fermat looks like it's Fermat, but it's pronounced Fermat. Pierre de Fermat was a French mathematician, and he's famous for driving other people crazy. He had a last theorem, which he kind of scrawled in the margins of a book. I have a neat little proof for this, and it was basically that something like the Pythagorean theorem, a squared plus b squared equals c squared, didn't work for any exponent bigger than 2. And for, centuries, mathematicians didn't have a proof, and he just said, oh, I have a nice little proof, and then at some point died and didn't tell anybody the proof. So it took years and years and years, like as in hundreds of years, and then it took a guy something like 10 years in his attic to write a proof, and then there was an error in it, and it was like awful, but then he fixed it, and they made a big documentary that pretty much only math majors watched. But anyway, another place Fermat decided to leave things off was his Fermat numbers. And Fermat numbers say that they're derived by saying 2 raised to the 2 to the n plus 1. And so, for example, the first Fermat number is 2 raised to the 2 to the 0 plus 1. So you have 2 to the 0 is 1, 2 to the 1 is 2, 2 plus 1 is 3. So the first one is 3. And it keeps going, and 3 happens to be prime. And then if you have the F1, that's when n equals 1, and you get 5, and that's prime. And F2 is 17, and that's prime. And F3 is 257, and that's prime. And F4 was 65,537, and that's prime. And then he got to F5, and it's 2 to the 2 to the 5, which is 2 to the 32 plus 1. And remember that he was doing all of his math by candlelight and with dipping a quill in ink and probably having to feed his dinosaur at the same time. And basically he said, oh, that's too big a number, whatever, I'm going to leave it alone. I'm not kidding. I'm not really making this up. He just said, too big. I don't know. I don't have the technology to figure it out. Somebody else will figure it out at some point, and left it. And so, of course, many years later, when somebody actually had the technology or the patience to multiply 2 times itself 32 times and then add 1, it turned out that equals 4,294,697,296 plus 1, which is 4,294,697,297, which is not prime. It's not prime. It's actually 641 times 6,700,417. I did not do any of this math myself. Of course, I looked it all up. There's no way I'm doing that by myself. Anyway, it's not prime. And so the point of this is why we have math induction is sometimes we need to prove things in math, like certain formulas or that certain relationships hold, and we need to have a really general case because proving it for a bunch of numbers is not enough. Saying that it's good up until here doesn't mean that it always works. And in math, the only way that we can have a rule is if it always works. Otherwise, we have to specify some sort of constraint. That's why when we were finding general solutions for trig functions, for trig equations, I always said, x equals whatever it is, like pi over 2 plus pi n, and then for n equals 1, 2, 3, 4, etc. And we always have to specify when is this true. Or we have to specify a domain. Oh, it's only true for this domain between this x and that x. Because in order to say that something is always true, we have to be able to prove it. And sometimes it's very difficult to prove that something is always true. And that's where proof by induction comes in, is it's very, very general, and it helps us prove that. Now, I'm doing something a little bit different. Normally, I just do notes, which is just notes, but I'm trying notes from another source. So this isn't my original note. I found this on the internet, and you'll find that I've included a blank for you so that if you want to print it out, you can, and you can write on it. all of the problems that you have are very similar. Some of these might actually be some of the problems that you have, and they're all very similar. And I'm going to take you through the steps. And then I think your homework, you have a bunch of problems that are actually from your textbook, from the pre-calc textbook. And I think I tell you to choose 3. So with that in mind, let's get started. So the first thing is there's some claim, and this has to do with series. It usually has to do with adding a bunch of numbers. And this says that if you add the odd numbers, 1 plus 3 plus 5 plus 7, etc., anything that's generated by this explicit formula, 2n minus 1, if you add up all those numbers, you get n squared, whatever it is. And so we start with a base case, and what a base case is, it says usually 0 or 1. In your case, it's always going to be 1. And so what we want to do is we look at this first term, and if we plug 1 in on the right side, then we should get whatever the first term is. And so if I plug, the right side says n squared, and so if I square whatever the first term is, I should get, in this case, or if I do whatever operation this is, I should get the first term. Well, 1 squared is 1. So that's my base case. And it's true. We always want to check to make sure that the formula actually works for the very first number in the series. Because if it doesn't work for the very first number, then it's garbage. Then, this says the left-hand side first and right-hand side. I actually do the opposite. What I do is I see what would happen if I plugged n plus 1, that's one more term. What if I just did one more generic term? And so what I do is I actually take whatever that formula is on the right-hand side, and I plug in n plus 1. And I get n plus 1 squared, which is n squared plus 2n plus 1. And then what I'm going to do is I'm going to see what would happen if I took here, if I plugged n plus 1 on this side and added it to the other side. So golden rule of algebra says whatever you do on the left side, you have to do on the right side. And so what if I did something like this? And the funny thing is sometimes they switch from n's to k's. That I'm not actually sure what the story is behind that, but you will see that in your textbook. And so I'm going to be adding something over here. And so instead of writing n like it is up there, I'm going to write n plus 1. So now I'm adding n plus 1 on the left side. That's what this thing is supposed to be, but I like to skip that step and just do it all at once. And so first I have to distribute, and I get 2n plus 2. And there's still a minus 1. And then when I collect like terms, I get 2n plus 1. And so that's what I'm going to add over here, 2n plus 1. And then I check to see if this right-hand side looks exactly like this right-hand side. And if they're exactly the same, then I'm done. And in this case, they are exactly the same. This and this, n squared plus 2n plus 1, n squared plus 2n plus 1. So I'm actually finished. That's my whole proof. The whole proof is I plug in the first term on the right side, and hopefully I get the same, I plug in 1. Let me make a note of that. Plug in 1 on the right side, and if I get the first term, then I'm good. Then I plug n plus 1 on the right side, whatever that right side is. And then I just evaluate to see what it equals. And then over here, what I did was I plug in n plus 1 on the left side. And then I check to see, and then I add it to the right side. Add to original right side. And they should be the same. The thing that you got in step 2 should be the same as what you do in step 3. This is step 3. And if they're the same, then you're done. I want to try another example. This is something that you really just have to practice a lot to really get the hang of. I usually spend like 2 or so days on this just to get practice. One day we just do some notes and you have a few homework problems. The next day you work on it in class and I walk around and help you out. And usually by the end of the second day, pretty much everybody is like an expert at doing this and they've presented answers to the class, but it does take a while to get used to. I'm not going to do this geometric proof thing. I don't really care. I'm going to look at this page. Claim. It says adding the even numbers 2 plus 4 plus 6 plus blah, blah, blah plus 2n. So anything that you get by plugging 2n, and that's equal to n times n plus 1. And so again, the very, very first thing we're going to do, our base case, is we're going to plug 1 in for n on the right-hand side. I'm going to plug in a 1. And that means I have 1 times 1 plus 1, which is 1 times 2, which is 2. And that's what my first term is. This number and this number should be the same. Check. Yay. Then I see, what do I get if I plug n plus 1 here on the right side? I'm going to plug in n plus 1. N plus 1, n plus 1, and then I just evaluate because it needs to be a little bit simpler. This becomes n plus 1, this becomes n plus 2. And I can multiply this out or I can leave it in factored form. I like to have both because I don't know what my ending is going to look like and I need to make sure that I see both forms so that I can compare regardless of what the end result is. So if it's in factored form at the end, I can see, okay, it matches this or not. If it's not in factored form, it's in expanded form, I can see if it matches. And this is n squared plus 3n plus 2. So then what I'm doing is I take my original series, 2 plus 4 plus 6 plus ... and I'm going to plug n plus 1 on my left side. N plus 1, and I get 2n plus 2. And there's actually no combining like terms, so that's easy. But I am going to distribute here n. Oops, that's n squared. That's messy. Let's try that again. N squared plus 2n. I'm going to do that because I want to, when I combine like terms, I want to make sure that I get the same thing or I don't get the same thing. Let's find out. And here's go. Into this. So I'm going to add 2n plus 2 to this side. Oh, why did I write 2n? That's n squared plus n. Miss Zach's making mistakes again. Oh no. Well, it should remind you of class when I'm talking too much and completely confuse myself. So I'm adding, I have n squared because I've distributed. N times n is n squared. N times 1 is n. I'm adding this 2n plus 2. And when I combine like terms, I get n squared plus 3n plus 2. Hey, this and this are the same. So I'm done. I just do check marks. I don't, you don't need to draw a little square or put a little symbol the way we did at the end of trig identities because this is the proof. All this work is the proof. We're not going to worry about a geometric proof. I'm actually going to turn the page and try another problem. And I think that, yeah, we'll do one more after that. These are actually going to look very similar to what's in your book because I found this on the internet, but it's entirely possible that the person that put this together is using the same book that we are. Hard to tell, but they look very similar. This is what happens when you add up all the numbers. You get this n times n plus 1 divided by 2, which should look very similar to the sum of an arithmetic series because this is very similar to an arithmetic series. Or it is an arithmetic series. So the base case, we're going to plug 1 in over here, and we should get a 1. When I plug 1 in for n, in the end, I should get whatever that first term is. That first term is a 1. So in the end, I should get a 1. And I get 1 times 2 divided by 2, which is just 1. Check. Now we see what happens if I plug n plus 1 in here. I like to use lots of parentheses. I do that even when I write. I use a lot of parentheses. And so this gives me n plus 1 times n plus 2 divided by 2. The other possibility is to multiply this out. That's n squared plus 3n plus 2 divided by 2. So I'm either going to get something that looks like that or something that looks like that. And then I'm going to go to my original sequence. Dot, plus dot, dot. And then instead of writing n, I'm going to have n plus 1. And I'm going to plug that in here. And then I'm going to also add it over here. But there's one issue, which is that this is a fraction and this is not a fraction. And so I'm going to do some distributing, and then I'm going to do some getting the same denominator. So I have this, and then I need to get the same denominator because it's just a 2. I'm going to multiply numerator and denominator by 2. There's a lot of distributing in some of these problems. I get 2n plus 2 over 2, and now I have two fractions that have the same denominator, and I can add, and I get n squared plus 3n plus 2 divided by 2, and it looks exactly like this one up here. Yay! All right, we're done. That's it. That's all there is to it. There's really no trick to it other than either getting the same denominator or keeping track of your n's and your n plus 1s. That can actually confuse people. Sometimes this part, because you're plugging in, and if there's already a plus 1, sometimes people forget to write the extra plus 1. So like this is some number and I'm adding 1. So this is some number adding 1, but some people forget this part because they're seeing so many plus 1s. I want to try one more, and this has to do with, nope, these are not the ones I want to do. Nope, those aren't the ones I want to do. I'm going to turn the page and try one more. What I want to do is showing, or maybe this is actually already written out for us. Is this? Oh yeah, actually it's already written out for us. So maybe I won't do one more. Maybe you can just read what it says. This is interesting. I believe there is a proof. I'm going to try to do it. It's about exponentials, and I think I have one somewhere. These are so similar to the ones that I do in class, it's not even funny. Yep, here's an exponential. We're going to look at 2 to the n. So if I add 1 plus 2 plus 2 squared plus 2 to the third plus dot 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 plus 2 to the n minus 1, it actually equals to 2 to the n minus 1. So here are the minus 1s in the exponent. Here it is not. And so the first thing I'm going to do is plug in a 1 here and see if I get my first term. 2 to the 1 minus 1. 2 to the 1 is 2, minus 1 is 1. This is a 1, this is a 1. So we're done. The next thing I'm going to do is plug in n plus 1 here. And this is actually going to be very easy because there's no simplifying. It's just 2 to the n plus 1. 2 to the n plus 1 minus 1. That's it, like this. Then I'm going to go back to my original original series. And I'm going to plug in n plus 1. And that has to equal whatever I get over here, I'm also going to add over here. I'm going to simplify this term. I have plus 1 minus 1, that becomes 2 to the n, like this. And so I'm going to add 2 to the n on this side. Now you may be saying, how in the world do you simplify that? Well, I'm going to group some like terms. I have 2 to the n plus 2 to the n. And I think, how many 2 to the n's do I have? Well, I have 2 of them. 2 times 2 to the n, because there's 2 of them. And then I remember from way back, probably Math 1 or 8th grade for some of you, maybe Math 2, some exponent rules that say that if you're multiplying the same base, you can actually add the exponents. So that becomes 2 to the n plus 1 minus the 1 out here, which is exactly the same thing that we got in step 2. So to review, because I added 2 to the n, I grouped them and I saw that I had 2 of them, so I wrote it as a multiplication problem instead of an addition problem. Kind of like you can write 2 plus 2 is the same as 2 times 2. Or 3 plus 3, there's 2 of them, is the same as 2 times 3. Or if I'm adding 10 plus 10, I can say there's 2 of them, so that's 2 times 10. In that same way, I said 2 to the n plus 2 to the n, there's 2 of them. But because we're talking about exponents and we're talking about bases, because the bases are exactly the same, here the bases are not the same, here they are, but here they're not, I can actually, because they're the same, I can add exponents and I get 2 to the n plus 1 with that minus 1 out here, which is exactly what we got in step 2. I'm going to end the video there because it's very, very long. If you have any questions, then please feel free to come to the class meeting on Tuesday at 3 o'clock. And then Thursday, we may or may not have a meeting. I'll be able to let you know by Wednesday. And then I think I'm going to start changing things for next week, where Tuesdays will be our big class meeting. And then Thursday, you'll be able to sign up for individual time slots if you need extra help. But other than that, it's going to be like I'm not going to just have it like free for all. You'll actually sign up for individual time slots so you can get some one-on-one attention. And then those of you taking AP tests this week, good luck. Make sure you study, but that you also get a good night's sleep and eat a good breakfast. And don't sweat it. I don't think that, I have a feeling that they're going to be very lenient in the grading because everybody knows that this school year has just been really crazy since March. So, but good luck to you. And again, you can always private message me through Canvas or email me or come to our class meetings. And the next one's Tuesday at 2. Good luck, and I hope to see you all soon.